Hello students, welcome back. Let us resume our discussion in section 3. We completed section 3.1, proof by manipulation, and subsection 3.2, proof by implication. Next one, subsection 3.3, proof by contradiction. Here's an example. Prove that A times B is 0, then either A is 0 or B is 0. I think we talked about it already, and we did it by direct proof, proof by implication. And I think we have to specify the domain. For example, if you allow A and B to be same matrices, then this may not be true. It has to be some kind of number. Complex number, that's okay too, but let's stick to real number system. So prove that AB is a real number and A times B is 0, then A is 0 or B is 0. Now, instead of going directly, you can use proof by contradiction. Let's assume this is false. Conclusion is false. So how do you negate the conclusion? Not equal to 0, negation. Not equal to 0, negation. Also, or becomes and. That's how you do the negation. And becomes or becomes and. All becomes some becomes all. So suppose that A is non-zero and B is also non-zero. In that case, what kind of contradiction can I take? A times B is 0, and we can divide by A, and we have 1 over A times 0, so B is 0. And that's a contradiction because we assume B is non-zero as well. Did you use A is non-zero? Yes, right here. Dividing by A, we used it. Did you use B is non-zero? Right here at the conclusion. You can do it the other way around too. You can divide by B and use this one first, and then you're going to get A equals 0, and that's going to be contradiction. You can do the same thing the other way around as well. In any case, it's a proof by contradiction. How about this? A is rational and B is irrational, then A plus B is irrational. If both are rational, then sum is rational, we know that. If one is rational, the other is irrational, then sum is irrational. How do you prove it? Again, let's use proof by contradiction. Let's assume A plus B is rational. Assume A plus B is rational. Then what can we do? A plus B is rational, so A plus B, and then subtract another rational number, which is A. What do you get? That's B. So rational minus rational should be rational, but that's an irrational number. There goes the contradiction. Here we go. B is A plus B minus A, so it's rational minus rational, so it should be rational, but B is assumed to be irrational, so there goes the contradiction. Next example. Again, this is an example of proof by contradiction, so go to the conclusion and negate it. We have to prove that this this series diverges, so we have to assume this converges. And then let's try to find some contradiction out of there. So if this converges, then this thing converges, and then subtract a convergence series, this one here. Then what do you get? So we get this. So convergent series minus convergent series should be convergent, but it diverges. So there goes a contradiction. Oh, I didn't give you the full proof here, so I shouldn't have shown you all those. I should have just stopped here. Oh well, alright. Next one I'm not going to forget. Let's see. This limit diverges and this limit converges. Prove that this limit diverges. Proof by contradiction, so you have to negate it. Suppose that this converges and try to find a contradiction. So assume this converges and then apply some limit rule. Try to get some contradiction out of there. Suppose that this limit converges, and then what do? I'll leave you there. So those are examples of proof by contradiction. Negate the conclusion, and then try to find a contradiction. Contradiction may come from one of the conditions, or it could be coming from some other known result, or even some axioms. In any case, find a contradiction. The use of proof by contradiction is very, very typical when you have to prove a non-existence. Suppose that it exists, name it somewhere, and then try to find a contradiction. Prove that the smallest positive real number does not exist. Prove that the largest real number does not exist. Prove that the open interval AB has neither the maximum does not exist, nor the minimum, and also the minimum does not exist. You see, these are all about proof of non-existence. In that case, proof by contradiction is very, very useful. Suppose that it exists, name it something, and then go from there. Let's see, in this case, what do? Smallest positive real number, let's say it's a minimum, m. So that's the smallest positive real number. And then what kind of contradiction can you find? Divide by 2, m over 2. Then that's a positive number too, because m is positive and dividing by positive numbers, so that's positive, but it's less than m. But did I say m is the smallest? There goes a contradiction. The smallest positive real number does not exist. How about the largest real number? Well, again, negates a conclusion. Suppose it exists, say the maximum, capital M, and then try to find out a counterexample, some contradictions there. And here we did dividing by 2. Yeah, divided by 2. So for the maximum, what if I multiply by 2? Will that work? Actually, it won't work. Suppose that the largest real number exists, capital M, and then find out even bigger. So how about 2m? It's not going to work in general, because what if m is negative? So you have to consider other cases as well. I'll stop there. You can make it work. And as for the interval, yeah, you'll have to do it twice. One for minimum and one for maximum. Suppose that the minimum exists, say small m. Suppose that the maximum exists, say capital M, and try to find something. Another typical use of proof by contradiction is the proof of uniqueness. Prove that there is one and only one additive identity. Prove that each real number x has only one additive inverse. Okay, again, uniqueness. Prove that an invertible function has only one inverse function. Again, uniqueness. Use the proof by contradiction. Suppose that there are more than one. Say 2 different inverse functions, 2 different additive inverses, 2 different additive identities, and then try to find out a contradiction. They turn out to be the same, or something like that. Here's an example. Suppose that there are 2 additive identities, say O1 and O2, and you're going to get this kind of nice contradiction. O1 is equal to O1 plus O2 because O2 is an additive identity, so adding that doesn't change. And that's equal to O2 because O1 is additive identity. Adding additive identity doesn't change anything. So what do you get? O1 and O2 are the same. Wait a minute. We assume they are different. There goes a contradiction. So one and only one additive identity. Given real number x, there's one and only one additive inverse. Okay, what if there are two? Instead of negative x, we may have something else, say y1 and y2. And then, how do you set those up? Well, stop the playback and try. Did you get it? Well, here's a solution. y1 is equal to y1 plus 0 because 0 is additive identity, and 0 can be rewritten as x plus y2. That's the key. y1 and y2, both of them show up now. And then use the associativity, y1 plus x, and that's 0. Remember, y1 and y2 are both additive inverses of x, two different additive inverses. And then this is 0, so 0 plus y2, but 0 doesn't change anything, so equal to y2. So what do you have? y1 and y2 are the same. There goes the contradiction. Of course, you can argue this as a direct proof, as a matter of fact, proof by algebraic manipulation. Suppose that there are y1 and y2, they end up being the same, so they're unique. You can argue like that, but over the years I found majority of the students feel a little more comfortable with doing exactly the same thing as a proof by contradiction. The same goes here. By the way, this notebook, this section, as a matter of fact, was originally written for analysis. So most of the examples here are coming for real numbers, not for integers. This 2 is an example of an analysis. There's one and only one inverse function, if inverse function exists. Never mind. I'm not going to go too deeply into that, so I'll leave that as an exercise for you. And if you're stuck, you can just move on because there's too much of an analysis, and this is number theory. And there are even other examples, of course. What about these? Prove that square root of 2 is not a rational number. It's an irrational number. How do you do that? And this is something we are going to do a little bit later in this course. It's a long proof, and it's pretty hard with multi-steps. So let's postpone that. How about the next one? Prove that the set of all real numbers is uncountable. In other words, I cannot list it as a sequence. So there's no sequence, xn, so that all the xn's cover R. By the way, with parentheses, it's a sequence. And then if you have, say for example, if you have a constant sequence, 1, 1, 1, 1, 1, 1, like that, then that's a sequence. But if you use this brace notation, then there's only one number, 1. So, and this parenthesis notation of sequence, and then this brace notation of image of those sequences are a little bit different. And then as for the proof, famous proof by diagonalization methods, well, I'm going to leave that as an exercise for you as well. I'm pretty sure you already went through that in Introduction to Proof class. Okay, so much for subsection 3.3.